My talk will be a little differently organized than most of the previous talks so far, in the sense that the first and the second hour will be somewhat similar. So I will have in each hour a more introductory part and then a more advanced part, if you wish. So in any case, I wish to talk about curves with a level structure and of order 2, and by this I mean essentially moduli spaces parameterizing curves with half periods. So the space that I would like to consider, at least in the first hour, is the so-called space of admissible double covers, and this is RG. So this is the parameter space of curves together with what is called classically a half period. So C is a smooth curve of genus G, and eta is non-zero. It's a half period. It's a non-zero element of H1 of C with coefficients in Z2. Of course, the information contained here is in the half period is this I can also write as the space. I mean, this half period gives rise to a line bundle. So this is a line bundle. I can view it as a line bundle, a non-trivial line bundle, which is a root of the trivial bundle. And so why would you study? Well, why would you study such a moduli space? This space RG sits interestingly between the moduli space of curves and the moduli space of abelian varieties. So there are two maps here. And the first map, well, the map to the moduli space of curves is obviously the forgetful map. So you can simply forget the half period. And the other map is the prim map. And this is really a map which was studied now for over 100 years, starting with Prim and Schottky. So what is this map? Yes, the space RG, the information contained in RG is of course the same as the information contained in a étale double cover. So I can say that RG also parameterizes étale double covers F from C tilde to F to C. So this is F is étale 2 to 1. And of course you can recover, if you have such a double cover, you can recover the point of order 2 in the Jacobian just by pushing forward the structural sheaf of C tilde. And this has this splits as OC plus the line bundle. And this line bundle is exactly this point of order 2. So these are étale double covers. And in that case, the genera here, so the curve C has genus G, and the curve C tilde has genus 2G minus 1. Yeah, so then perhaps I should just define this prim map. So you consider the norm map associated to this cover, and you can do this in any degree, and I do it in degree 2G minus 2. Yeah, so this is simply, you just take a divisor consisting of points on C tilde, and you look at the divisor, at the images under the map F. This is a norm map. And obviously distinguished line bundle, namely the canonical bundle, or if you wish, the origin. And you look at the inverse image of this, and the inverse image splits into two components depending on the parity. And you can now decide to work with the odd or the even component, and most people work with the even component. And so if you look at the space, so the prim variety will be associated to C and eta, will be the set of line bundles in, so these are line bundles of degree 2G minus 2 on C tilde, which have canonical norm, and they have an even number of sections. Generically, they have no sections. Right? So this is a torus, and clearly, so this is 2G minus 1 dimensional, this is G dimensional, so the kernel is G minus 1 dimensional, But the beauty of it is that this is a principally polarized abelian variety, and it comes with a theta divisor, which Mumford denoted it as the chi divisor, so I will use the tech notation here. So the chi divisor has a very nice interpretation. So this is the line bundles L in the prime variety with an extra condition, namely that A0 of L has at least one section, but then if it has one section, then it has two sections, at least. So this is very nice, and it mirrors in some way the situation for Jacobians via the Riemann singularity theorem, where you have a theta divisor also has an interpretation in terms of Brill-Noether theory, and the extra condition is, of course, this norm condition. You can go further. You can study the singularities of the theta divisor of prime variety, and they also have a similar interpretation. You just look at more sections here, just like a situation which mirrors very nicely the case of Jacobians. So why study RG? Yeah, so why is this space called RG? So this is, I think, I understand, I recently learned that this is due to Beauville, and it means revêtement. It's in French, so it's clear that this has to do with coverings. And why study RG? Well, so first of all, classically, because of the Schottky problem. RG is central to several classical approaches to the Schottky problem. And the idea is that there are more prime varieties than Jacobians. The dimension of RG, so the dimension RG, this is really an état cover, so this has dimension 3G minus 3. And this has dimension G minus 1 choose 2. You can see that there are simply more prime varieties than Jacobians. Right? So Mg minus 1 sits here. And in fact, Mg minus 1 is a subset of the image of the prime map. Perhaps I should call this prime G. And the Jacobians really are in the boundary of the prime locus. So if you want to understand abelian varieties, you have a better chance of writing down the generic abelian variety as a prime variety. And this indeed happens at least in small genus. So you have a well-known result that prime G is a dominant map for genus less than or equal to 6, which is the only case it could possibly be dominant based on dimension calculations. So that is very nice to understand the generic abelian variety of dimension G. And then for genus greater than 7, this map is actually generically finite. But never finite. So you cannot recover the every prime variety from every pair C eta from the prime variety, but you can recover the generic one. So in other words, prime Torelli fails, and the non-injectivity locus of the prime map is subject to a very interesting conjecture due to Donaghy. This is the Donaghy conjecture. And I don't think I want to enter in this. There is enormous literature on ways to prove this conjecture. Okay, so why study this RG? So then another reason, which I should mention now, prime varieties have been very important to study rationality questions for threefolds. Or more generally, conic bundles. And I mean, the classical story, which probably many people know, or they should know, is that of the cubic threefold. This is a unirational variety, but not rational in general. And this was one of the first examples, due to Clemens and Griffiths, of a threefold which is unirational but not rational. And that was done by considering the intermediate Jacobian of X. And this is an element in A5. And so it is really a prime variety. It's a prime variety. It's an element of R6. And they have a rationality criterion. So Clemens and Griffiths, rationality criterion that X is rational if and only if the intermediate Jacobian is in the closure of the Jacobian locus, which is, of course, very, very natural. I mean, if it's a rational variety, then it has to be obtained from P3 by blowing up points or curves. And the only thing you pick up in intermediate Jacobian is a Jacobian of that curve, more or less. And so Miles seem to disagree. But it's a statement. To me, it looks a criterion. But so in any case, so the generic one, the generic cubic threefold is a prime variety. You recognize that it's not a Jacobian by having this interpretation of the theta divisor. So basically, you study the singularities of the theta divisor, and then you can see that when X is general, this is not a Jacobian.
Maybe I have the same question too. Is rationality criterion for what? For 21 also?
No, actually, so I wrote here. So this is a cubic threefold.
Cubic threefold is never rational.
Yes, that's right. So, okay, well, it is correct, yes. What I'm saying, what I'm writing here is correct, yes. It's never rational because it is the prime. Yeah, okay. So I don't think I will change this. It's a yes. So what I was saying is that the cubic threefold, it is always a prime variety, yes. If it was rational, then it would be a Jacobian, but it is never a Jacobian, yes. Yes.
The intermediate Jacobian.
Yes.
Jacobian,
that's right. Yes. Yes. Okay, so I don't think I want to go in this direction. I just mentioned that there is a, yeah, this has been also used to produce examples of stable rational but not rational varieties and so on. So there is really a lot of geometry in this direction. Okay, so then the next question I want to briefly address is the one of description of the space Rg. So as I said, Rg was used to describe Ag minus 1. And then you have here a bunch of results. So how about birational geometry? It is known, so Rg is rational for small values of G. And this is for G2, 3, and 4. And then I would put here Dolgachev for genus 2 and 3, but genus 2 surely was known to Kobel. And genus 4 is a very nice paper by Catalina. And then it's unirational for the next 3 values. And now the story becomes much more complicated. Actually, even genus 3 and 4 is not entirely is not entirely obvious. So for G is 5. This is a recent result of Vera. And there is another paper by another proof, in fact, by Izadi and Sankaran in the same year, more or less. Then genus 6, of course, is a very famous picture. And this is incredibly beautiful because the dimension of these spaces is equal for G equals 6. So you have a map, the pre-map from R6 to A5. These are both 15-dimensional varieties. And it is a generically finite cover of degree 27. And the monodromy is exactly the one of the lines on the cubic surface. This is the Weil group of E6. But this is all very complicated. This is, it would take me a lecture to explain this genus 6 situation. This is not, the cubic surfaces are not anywhere in the picture in an obvious way. They are somewhere in the boundary of this picture. So this is a very nice result. This is due to Donaghy and Donaghy-Smith. And also R6 is unirational. So then it follows that A5 is unirational. But here I mean, for completeness, this picture is so rich that the same thing can be proved in 3 completely different ways. And so there is another proof due to Vera, So Donaghy uses the geometry of these quartic double solids. So this is a proof using quartic double solids, whatever they are sort of certain double covers. A completely different proof using Enriquez surfaces is due to Vera, appeared around the same time. And then the most famous proof probably is the one due to Mori and Mukai, which is again yet different. So it's a very rich picture that, and you have these three approaches, and it's not clear at all how to go from one to the other. And then finally G equals 7. So this is due to Vera, the same result, and this is not even published yet. But this is also incredible richness. It's a very nice argument. And I will talk more about the next case perhaps in the second hour, in genus 8. Yes, the result is yes, is rational, unirational, yeah. And I will talk. I will go. I'm not going to review this this picture. No.
What is the degree of the prime map? You said it's generically finite. The degree is not the degree of generic degree of the image.
I mean, it's 1.
Generically 1 of us.
Generically 1, so not generically finite. You told.
Oh, I see. You are right. Of course. Thank you. Generically injective. Yes, and this is due to Friedman and Smith, and possibly to Shokurov as well. Okay, so essentially what I would like to do is to so talk about kind of the mathematics surrounding a following theorem. So which I proved sometime last year. The question, of course, you don't expect this to hold on for much longer. You have experience from moduli space of curves or of abelian varieties or K-free surfaces that for genus 13 or higher, actually strictly, the moduli suitable compactification of RG is a variety of general type. But I mean, I will sort of present other things that go into proving this. In particular, I will talk in some detail about a conjecture that I proposed for syzygies of prime varieties or prime canonical curves, which is a kind of a generalization of or an analog of the classical Green conjecture. And proving this conjecture for some values is important for proving this theorem. Let me now, before getting into this theorem, let me say a couple of things about how can one compactify moduli of curves with level 2 structure. So I put here a bar, and I should explain this. And this discussion, I mean, will be at a rather leisurely pace, and so it will be sort of educational. And the same approach can be taken for compactifying other moduli spaces, for instance, spin moduli spaces or moduli spaces of curves with high level structure, generalizations of the modular curves, and so on. So the problem is, of course, that you have here a Galois cover of the moduli space of curves. So the degree of this is, of course, the number of points of order 2 in the Jacobian of the curve. It's a finite, it's an étal cover, yes, an étal cover of degree 2 to the 2g minus 1. And this sits inside the moduli space of stable curves. And you would like to have a suitable compactification here. And this, of course, exists. You could simply take the normalization of mg bar in the function field of Rg. But if you take this definition, it's not clear that it has a modular meaning. So, however, there is a good modular solution to this problem. And you can take Rg bar to be the stack, if you wish, of admissible double covers. So I just to write something here, I can write this as mg BZ2. Yeah, so if you wish, it's a sort of twisted stable maps, if you to use a fancy terminology, which is not really necessary in this case, into the classifying space of Z2. So this is also the same thing as this concept of stable prime curves, which I'm going to explain now. So I'm just going to give you the points of this moduli space, and this état cover now extends to a finite but ramified cover. So what are these prime curves? So definition here. So a stable prime curve of genus G is a triple consisting of a curve, a line bundle, and a morphism of sheaves. So here X is what is called a quasi-stable curve. So quasi-stable curve is a nodal curve, of genus G. It's a nodal curve which is almost stable, which can have disjoint exceptional components. And the exceptional components, these are rational components meeting the curve in the rest of the curve in exactly 2 points. So this would not be allowed in the stable world, right? But you have a stable curve. You have a stable curve like this. And then you can, well, I can make it, for instance, like this. And then I can choose to blow up, so to speak, these nodes or not, right? And if I blow them up, then I can insert exceptional components. So I can have something like this. So I could just insert here a rational component. So this is a rational component which I inserted. This is a P1, right? And this would not be stable. And then to stabilize it, I would just contract this, and I would get back the original curve, right? So this would meet the rest of the curve only in 2 points. So it's really a very mild modification of the concept of a stable curve. And now these people who work in minimal model of a moduli space of curves, they have used this terminology. They have taken over this terminology of quasi-stable curve, and they call it something else, which is very unfortunate, of course, because this already existed. But so I will stick to this. Then the point eta is a line bundle of degree G minus 1. It's a locally free sheaf on this quasi-stable curve with the property that, I'm sorry, degree 0. With the property that eta restricted to each exceptional component is simply O of 1. And then finally, beta is a sheaf homomorphism from the square of eta into OX with the property that beta is non-zero on any non-exceptional component. Of course, it could hardly be 0 on exceptional components because I have here O of 2 going into O, right? So there are no such morphisms. But on non-exceptional components, it is 0. So now this is a combinatorial data. So if you give me a dual graph, a stable curve, you have this nice combinatorial question, which was solved in some sense by Caporaso, of describing the fibers of this map. And this also can be used to understand completely the ramification of this map. And the situation is relatively simple. So let's do this.
Sorry to be stupid. I don't know what big 0 is.
Yes, it's big 0, right? So the reason I introduce these quasi-stable curves is to preserve this requirement of local freeness. That's why I don't have torsion-free sheaves.
Yes, but what is big 0?
Oh, yes, what is big 0? Big 0 is total degree. Total degree bundles, locally free bundles of total degree. This is not, yeah.
So it has +1 on those curves, and therefore it has -1 on some other curves.
well, I mean, the total is not quite, but the sum is 0, yeah. So here's an example. It's a simple example, but it is important to understand the ramification of pi. So I take a curve. So mg bar has these boundary divisors corresponding to possibilities of degeneration of curves of genus G in codimension 1. And then I take a generic point of delta 0. So this is a curve like this. So it's a curve obtained from a curve of genus G minus 1 by taking 2 points and identifying them. Yeah, so CYQ, if you wish, is a two-pointed curve of genus G minus 1. Smooth one, right? So this is CYQ. I just note the points that I identified. And this is the normalization map. And then I would like to understand the fiber over CYQ. So then you have this problem of describing this data over this curve. So if I take a point x, eta, beta here, then I have 3 possibilities. Actually, I have 2 possibilities at first. The first possibility is that x is actually CYQ. So I don't insert any rational component. So I have a line bundle of degree. I have a line bundle on this curve itself. And then, of course, there is this usual exact sequence at the level of Picard groups. So here I have the Picard group of x goes into Picard group of C, and this is surjective. So this is the pullback. And here I should put a copy of K, right? But in fact, since I take points of order 2 here, I will end up with Z2. Okay, so and then I have this eta is a line bundle on X, and I call eta C the pullback. And now I have 2 cases. So the first case is that I have a line bundle on this one nodal curve, but now I distinguish 2 cases depending on whether this pullback to the normalization is a trivial bundle or not. So the first case is when eta C is non-trivial. It's really a non-trivial bundle. It's a point of order 2. And then I basically have also the choice. I have here a Z2, as you can see. So I have a choice of gluing these fibers of this line bundle in 2 ways so that I get an element in RG bar. And I call the locus of such curve delta 0 prime. So delta 0 prime is the locus of such curves CYQ, where and together with eta C, which is a root of the trivial bundle, plus the choice of the gluing. And this is a divisor in RG bar. And so to be educational until the end, I can also tell you what is in the level of double covers, what this is. So what is the information contained here? The information is that of an étal cover of the curve of genus G minus 1. So this is also so delta 0 prime. I can also represent it like this. So I have a curve of genus G minus 1. This is C, yeah, and I have 2 points, Y and Q. And now I take the étal double cover given by this point. So this I never get completely right, but now I will try again. So here I have now these points, the fibers Y1, Y2, Q1, and Q2. And to get an admissible cover now, I do the obvious thing. I will identify the nodes, the points Y and Q, to obtain CYQ. And then, of course, I will identify the points in pairs. I will identify Y2 and Q1 and Y1 and Q2. And I never succeeded in drawing this picture successfully on the blackboard. And this time it will be no different. So I will do something like this. I'm sorry, this is really not very good. But this is Y2 identified with Q1 and Y1 identified with Q2. In any case, at least you should convince yourself that the genus is right. And of course, you have now a Z2 freedom, right, in labeling Y and Q, Y1, Y2, and Q1, Q2 respectively. And that is exactly reflected in having a kernel here. So that is also a divisor in delta. That is the divisor in delta 0 in RG. That was the first case. The second case is where we don't blow up X, CYQ, but the line bundle eta C is trivial. And then we get another divisor. This is delta 0, I call it double prime. So this is the locus of curves like this. And now eta C is a trivial bundle on the normalization. But so eta C is trivial, but there is a unique choice, a unique way of gluing the fibers such that I get a non-trivial bundle on X, right? Plus the unique choice of gluing eta C at Y and Q such that eta is non-trivial. Yes, clearly there are two ways, and one produces a trivial bundle, the other one a non-trivial bundle. And in terms of coverings, this is, so I can also represent this. So I have C here, and I have now, well, I have the trivial bundle, so this is going to produce the trivial cover, of course. So I have two copies, C1 and C2. So here is Y, here is Q, here is Y1, Y2, Q1, Q2. And then, so this is, this is genus G minus 1, right? And now to make a covering out of this, an admissible cover, you will identify the points in pairs again. And you get something like this. So here is CYQ. And yeah, so I take two copies of C. So this is C1, here is C2. And I identify Y2 with Q1 and Y1 with Q2. So this is a very classical picture. It's called the Wirtinger cover. This is really 19th century Wirtinger cover. It's a very simple degeneration, point of RG, and it fills up a divisor. Yes? And finally, I have a possibility that X is not equal to CYQ. So since I have one node, from the definition of quasi-stable curve, I can blow up only that node only once. So if X is different from CYQ, then of course I know what it is. Then it is C. And then I insert a rational curve. And this is this union. Then X is equal to R union at Y and Q of C. And now you have, unfortunately I erased the definition. It was not so good. So I'm looking for a line bundle of total degree 0 here. So on this P1 it is O of 1. And then on C it has to be a bundle of degree -1. And because of the third condition of the existence of this Schiff homomorphism, this bundle must be a root of O of minus Y minus Q. And then there is no more choice needed in gluing the fibers of this bundle. So I get a third boundary divisor in this way. And this I will call delta 0 ramified, because this will turn out to be the ramification locus. So this is the locus of such points. So this is R, C, Y, Q, where eta R is fixed, and eta C is a root of O of minus Y minus Q. And to have a picture, a corresponding picture, I can draw now. So what does this correspond to? So I have here a curve of genus G minus 1 with the 2 points. But now I take a root. Eta squared is O of minus Y minus Q, so I have ramification at the points Y and Q, right? So I take a ramified, this will induce a covering which is ramified over Y and Q, so I have only 2 points here, Y bar and Q bar. And so this curve has genus G minus 1, so, and this will have genus 2G minus 2 from the Hurwitz-Zeuthen formula. And then I can consider the following cover, identify again CYQ, Y and Q to obtain CYQ. And then now this is again almost impossible for me at least to draw. I have this curve on top, Yeah, so I identify these points. I want to identify the other ones as well. So to bring the cover, yeah, I still haven't found a way of drawing this convincingly. So I don't know what to do. I will just do like this. This is, yeah, it doesn't even look double cover. I'm sorry. But you understand, right? So it's a this is C bar, if you wish. And you get certainly a curve. So it was genus 2G minus 2. I define 2 points and get a curve genus 2G minus 1. So this is a very nice picture, at least in codimension 1, and you can iterate this. You can go further into the boundary. And if you read Caporazzo's papers on describing the fibers of this prime map or spin or the spin moduli space, which is essentially roots of the canonical bundle, you will get very nice combinatorics. Okay.
But you have to say it's ramified.
Yes. So exactly right. So now, if you right, thank you very much. So this is exactly the ramification divisor. Is the ramification divisor of pi. And you can also see this if you count how many points in the fiber do you have over the 3 divisors. Over delta 0 double prime, you clearly have 1. Over delta 0 prime, you have roots, the ways of choosing a root of O, which is 2 to the 2G minus 2 minus 1 multiplied by 2. And here you just have roots of these bundles, which is 2 to the 2G minus 2. And then you can see that to get the total number, which is the degree of pi, you have you have here simple ramification. That is a kind of a simple-minded way of convincing yourself that this is the ramification divisor. So what I proved by doing these 3 pictures is that if I look at the map, this ramified cover from Rg to Mg, the pullback of this boundary divisor delta 0, so the smaller deltas will denote classes, and capital deltas will denote divisors, will be delta 0 prime plus delta 0 double prime plus 2 times the class of this ramification divisor. No, they are finite of Rg. This is a smooth délignement for stack. I mean, we have this Z2 condition. Which imposes finiteness. Okay.
So you know, I wanted to say the covering, the map of the covering on the curves is ramified at each of those branches.
Yes, it is ramified. That's what I tried to.
Yeah, but also on that curve there. It's really the
yes.
half of 1 quotient of.
That's right. Yeah. So I sort of made. I'm sorry. I just cannot draw this. Right. So I don't. There must be a way. I mean, there is a. I saw a paper of Beauville where he managed to draw this, but I've forgotten the picture. This is. There's no chance I will do it now.
From the point of view of the prim map, this is really in the interior.
This is really in the interior. That's right. Exactly. That's. Yes. That's a good point. Yes. That's right. Whereas here, the prim map is the Jacobian of the original curve C. So that's why this was a very simple degeneration, and this trick was used for proving many results about, for instance, the generic injectivity of the prim map. This was used by Friedman and Smith by doing such a degeneration, if I remember correctly.
These pictures were in papers of Beauville.
Yes.
About 20 years before.
Well, that's why they are called Beauville admissible covers. Yes. Okay. So then. Okay, so the next issue I want to talk about is the canonical class. So I mean, this should be very easy now because I have described the ramification of this. Yes, I'm sort of ignoring the other boundary divisors, but the picture is quite simple over other boundary divisors, and I will just ignore this side of the story. So the canonical divisor of Rg is the pullback of the canonical divisor of the moduli space of curves plus delta 0 ramified. And the canonical class of MGs, has been computed by Mumford. It's a very famous Riemann-Roch style calculation, and it's 13 times the Hodge class minus 2 times delta 0 minus 3 times delta 1 minus 2 times delta 2, and the other one are also all 2. So this is the Hodge class. And then I can just compute the canonical class of RG, and I get here 13 lambda. I can use the pullback formula, minus 2 times delta 0 prime plus delta 0 double prime. And now comes this is minus 3 times delta 0 ramified, and minus other boundary components. And this is very important, this 3 here, which of course comes from the ramification. And this will change the situation compared to the moduli space of curves. Since you take this ramified cover, the canonical bundle on RG, of course, has stronger positivity properties than MG. And of course, when MG is of general type, RG is of general type. And MG is known to be of general type for genus 22 or higher. But in fact, you can do better for the moduli space of prime varieties because of this branching. So now I will just say that. So the question here is, So to when is this class positive? And this is kind of a modular form problem, right? So are there modular forms on this moduli space of curves with a half period of weight 13, which vanish with order 2 at infinity? This is a kind of a question which was addressed by Mumford and by Harrison Mumford in the case of moduli space of curves. And the method that I use for proving general typeness of RG or of the moduli space of spin varieties later on is a similar method. And I'm just going to construct, by using algebraic geometry, by using the Rie geometry of prime varieties, a divisor, an explicit representative, a Weil divisor which is in this class, an effective Weil divisor which is in this class. And now I have to discuss a technical issue, but now since I have 2 hours, usually I skip this, but I can discuss this. It's a very important issue, the issue of singularities. And this is joint work with Catalina Lubic, who was a postdoc in the group of Klaus Hulek. So the problem is that this space is not a smooth space, and Kodaira dimension is defined as a Kodaira dimension of the singularization. And if I create a divisor, a Weil divisor, which has class, this class, the canonical class, and I do this by geometry, then I have a priori no guarantee that that form. So this will correspond to a canonical form or a pluricanonical form on the smooth part of this moduli space, but there is no guarantee that this will extend to the desingularization. So you have to study the singularities of the moduli space, and the result that we prove is that if you have any resolution of singularities, so this is for genus at least 4, there exists an isomorphism. This induces an isomorphism at the space of pluricanonical forms. So any form extends to the desingularization. So there was, yesterday Radu Laza mentioned something similar for, in passing mentioned something similar for moduli space of abelian varieties, where Hulek, Gritsenko, and Sankaran proved a similar result by showing that the singularities of the moduli space are canonical, and then such an extension is automatic. In this case, we are not so lucky. The singularities of the moduli space RG are not canonical. So there will be local obstructions for form to lift. But what we show is that these are not global obstructions. So first of all, we classify. So that is the program. We classify all.
I'm sorry, reg just means the non-singular.
Reg means the non-singular, regular, yeah. That's right, regular, so smooth.
But you said it was a smooth Deligne-Mumford stack.
Yeah, but this is a question about the space, right? So I take, essentially, yeah.
It has all before singularity.
Yeah, no, this is like a classical varieties. I take a form, so RG, I view it as a coarse moduli space, right? And then I take a form defined on the smooth part, and I want to say that this will lift to a form on any desingularization.
But
so
RG bar has quotient singularity.
Yes, and I'm going to say this in right now. So we will classify describe all non-canonical singularities, and indeed Rg bar has quotient singularities. So in a neighborhood of a point, if I take a point, locally, this is Rg bar is C to the 3, well, yeah, I really don't know how much I need characteristic 0, but yeah, I know I do need characteristic 0. So C to the 3G minus 3, this is the, if you wish, you identify this with the tangent space, modified out by the automorphism group of X eta beta. So I didn't tell you what is an automorphism of such a triple, but you can understand, I think you can figure this out by yourself. So essentially, yeah, you basically want automorphisms of the stable curves which are compatible with the sheaf and the homomorphism, so you have a diagram that commutes. And this is a finite group. It's a finite group, but in general it's a wild group. It's not very easy, if I give you a dual graph, it's not easy to describe it. So this is a result, actually it was done mainly by my coworker Catalina Lubic, and this is really, I was very impressed with this classification result. Because to classify, so basically to list all the possible automorphisms, all the possible ways in which automorphisms act on the deformation space of the prim curve, this is kind of combinatorial a very challenging problem. How is this classification done? The classification is done, of course, via the Reed-Shepard-Baron-Tye criterion. So I will also mention this. So I have an automorphism, so let's call it sigma of order n. Then this will act, this action will act on the versal deformation space, on the tangent space, and the eigenvalues of the action will be zeta n a1, if you wish, zeta n a to the a3g minus 3, where zeta n is e to the 2 pi I n. And then, I define the age of sigma to be the sum of the ai divided by n. And what is the Reed-Shepard-Baron-Tye criterion says is that whenever the age is less than or equal to 1, greater than equal to 1, yeah, the singularity is canonical. So x eta beta, yeah, the singularities are canonical. So there are no problems locally. So now the secret is to get rid of, here you have, of course, a jungle of cases, right? I mean, you have to do this over all possible graphs. And now the secret is to eliminate the vast majority of these cases, to compute the age and say it's sufficiently large, so we don't have to worry about them. But then we have a locus of non-canonical singularities, and there you do have local obstructions, and then we lift those forms by hand to the singularization of Rg bar. But for this, you really have to describe this locus, and then the theorem is that the non-canonical locus, the non-canonical singular locus of Rg is equal to the locus of curves x eta beta, which are where there exists an elliptic component. So there exists a subcurve consisting of an elliptic component and the rest. So I have here E, and here is, I don't know, C, but C can be also singular. But E is elliptic. It has automorphism Z6. So the automorphism of E is Z6. And eta is the restriction of eta, so there is this line bundle. Eta E is trivial. And the automorphism sigma is of order 3 or 6, of course. Maybe I should say this, yeah. And exists sigma, an automorphism of the triple x eta beta, and the order is 3 or 6. I'm going to write this here. Order of sigma is either 3 or 6. So this is a simple list, because we can construct now, so we have a simple locus in the moduli space of prime varieties, and we construct a resolution of this locus, which will show that the local obstructions are not global obstructions. So Catalina Lubic had a similar theorem, and so this was actually her thesis, for the moduli space of spin varieties. And people say, well, there is no difference between moduli of spin varieties, which are roots of the canonical bundle, and moduli of prime varieties, which are roots of the trivial bundle. Well, this is, of course, kind of superficial. In particular, this theorem describing the non-canonical singular locus looks completely different for the spin moduli space. It's really so the two spaces are very, very different in nature. But in any case, the outcome is the same, that on both cases, the spin and the premoduli space, you have this lifting theorem. And then you can really not worry about singularities.
So we're in codimension 2? Or
yes, codimension 2, yeah.
and so it's the third one.
Yes, yes, yes. So unfortunately, I don't have such a theorem for high. I have such a theorem for level 3, perhaps, and I certainly don't have such a theorem for higher level. So I just, it is, the number of possibilities is just tremendous. So it's not particularly difficult, but I still cannot put all the things together. So to prove such a theorem for these generalizations of the modular curve. So the problem, of course, is that there are just more and more non-canonical singularities as you increase the level. Okay, so now I can go to the next topic, which is geometric cycles in RG. Geometric cycles. So I had this canonical class, which I just erased, and I would like to construct, to have a theory of constructing interesting geometric cycles on the moduli space of prime varieties. And so my ideology for treating such problems is to always look at the syzygies of the objects you parameterize, not to make any choices, any other choices than the choice given to you by the points of the moduli space. And here the points are really a pair C eta, which corresponds to an eta double cover. So you have nothing else, right? Of course, each curve will carry lots of other linear systems. It will have a lot of extrinsic geometry. But I want to ignore this completely. And I want to write down the Kosul complex for this object. So I'm just going to write down the Kosul complex. And of course, you have to keep in, for the canonical bundle, and you have to keep in mind that the canonical differentials on the curve on top split. There is a Z2 action, of course, and they split into a +1 space and a -1 space. So this has dimension G, and this has dimension G -1, and this, of course, has dimension 2G -1. So this is the +1 space, and this is the -1 space. And now when I write down the Kosul complex, I'm going to say this exactly what I mean by this. The Kosul complex will also split in 3 parts. It will be a Kosul complex. So I just write this imprecisely. So the Kosul geometry of RG, of MG, which is the Kosul complex of the canonical bundle of C itself. And this will lead me to MG. So there is nothing new here, right? I mean, basically, you can prove in this way the classical theorem of Harris and Mumford about general tightness. And in fact, I did that. This is in a paper on Archive last year. Using Green's conjecture, but there is nothing new about RG you're going to get in this way. Then you can also get the Kosul complex of Kc plus eta, and this will give me essentially the case of RG, at least in one case, in even genus. And then there is something that at first sight looks rather frightening. This is this mixed Kosul cohomology, where the two parts mix. So you look at the Kosul cohomology of Kc with coefficients in Kc plus eta, and you see, oh, my God, there will be no geometry here. But actually, this case is easy, and this takes care of RG for genus, for odd genus. And this takes care of RG for even genus. So I will not talk about this mixed part at all today. And I will concentrate on this part, and I will talk about sort of a conjecture, which is the Prim-Green conjecture. Yes. Yes, so basically the idea is very similar to what you do for arbitrary varieties. You look at the curve, which is embedded by this linear system, by the prime-canonical linear system, into projective space Pg minus 2. So this embedding is given by a linear system of dimension G minus 2 and degree 2G minus 2. This is called the prime-canonical linear system. And then I look at the corresponding polynomial ring in G minus 1 letters. And then I look at the ideal of the curve in here. And I resolve this ideal as a graded ideal. Yeah, this is a free resolution. It's a minimal free resolution. And then now I say that, well, following Green and Lazarsfeld, I say that K plus eta, this bundle, satisfies Green-Lazarsfeld property and I, if and only if, the first I pieces of this resolution are as simple as possible. Fj is a sum of copies of S shifted by j minus 2 for j less than I. So let me explain this. So that means that you really live in an ideal world, at least up to the jth step. So n0 actually, so yeah, so that means n0 is not incorporated in this definition. N0 simply means that Kc plus eta is projectively normal. But then n1 means that the prime-canonical curve is cut out by quadrics So this is a finite number of quadrics which you can compute because it's projectively normal. And then this means n1. Then n2 means that the syzygies between these quadrics are linear. Then n3 means that the syzygies between the syzygies are linear, and so on. And this goes on so F2 parameterizes the relation between the quadrics, F3 parameterizes the relations between the relations, and this goes on for I steps, right? So, and then you are in the really, you really understand the geometry of the curve if you can prove that of the prime-canonical curve, if you can prove that this happens for some I sufficiently high. And the question of how high I can be is exactly the object of the next. So here is the next theorem, which I want to mention, is that basically, let me just state it. So there are vector bundles A and B over. So now I will take G to be even. That's what I said, and I choose to write it as 2i plus 6 over Rg over R2i plus 6 of the same rank. Together with the morphism such that, yeah, so I will go 3 minutes over time. I'm happy to have a shorter second lecture. Together with a morphism such that at least over the inverse image of mg union delta 0, we have the following situation. The degeneracy locus of this phi is precisely the locus of those C eta with the property that Kc plus eta fails Ni. So that is the reasonable thing to expect, that for genus 2i plus 6, the generic prime-canonical curve does satisfy property Ni, and that this morphism is generically non-degenerate. And then I can compute the class of this. So, and I call this locus Zi. the virtual class of this locus, well, this is of course the main point of this theorem is that I can do this over the boundary. I mean, over the interior, this is not difficult. But you can compactify this, and you need this to compute the Chern, I mean, to do intersection theory. This is equal to a certain binomial coefficient times 3 times 2i plus 7 divided by I plus 3 lambda minus, and now comes an expression here. The calculation is, so once you extend the bundles in a modular fashion, then the calculation is not difficult, but the extension is a little tricky. Algebra, the canonical class, as a positive combination, a positive rational combination of this virtual class and other boundaries. And maybe the Hodge class as well, which is also positive. So, of course, the problem here is that this virtual class may not be, may be virtual, may not be a class at all. Maybe simply, yeah, it's a class, but maybe it may not be an effective divisor, may not be the class of an effective divisor. And so provided now that ZGI, I'm sorry, this I call, yeah, ZG is okay. This is ZG. ZG is a divisor. Then you have that RG is of general type. For G greater than 14, right? And in fact, you also get that the Kodaira dimension of R12 is greater than or equal to 0. Because that will be exactly I equals 3. So now you have this issue, of course. So that is the intersection theory part, and I don't think I will comment on this more. There is this issue now of transversality here, and what these bundles mean. And this is exactly the spring-ring conjecture, and so I will talk about that after the break.